Okay, so what I want to do today is, let's get rid of this. I want to give an example of using this Skein relationship. Let me just show it on the computer. So we've been talking, we defined the Jones polynomial from the Kaufman bracket, and we did calculations, and there are also new calculations. And the other thing in response to feedback is I've tried to make the questions a bit more easy and a bit more computational on the sheets, both last week and this week. So, for example, the first question on sheet 5 is purely diagrammatic. There are no calculations to do. So I want to explain how to use this rule in practice. This doesn't relate to the Kaufman bracket. This is directly a formula directly for the Jones polynomial. What happens when you reverse a crossing of a link or not to the Jones polynomial. So I want to apply that formula now. Before I hide this screen, I just want to say that you need to sort of remember the distinction between L plus and L minus. So when we talk about the Jones polynomial, things are oriented. Kaufman bracket, we didn't need the orientation. So the Jones polynomial, everything has to be oriented. So if it's a link, every component has to be oriented. Even a knot, you have to orient it. So to apply this formula at least. I mean, the Jones polynomial won't depend upon the orientation if it's a knot, but to apply this formula, you need orientations. So if you see the L plus, that corresponds to, I like to think of the overpass as the x-axis normally. So if you think of the overpass as the x-axis, the y-axis is underneath and it's going in the right direction. So that for me is L plus. So if you're given a crossing, you have to decide if you're given a knot with an orientation and you fix the crossing, you have to decide whether that crossing is of type L plus or L minus in order to apply this formula. If it's of type L minus, then you're looking to find that, and you express it in terms of this and this. If it's a plus thing, you can express the knot you want in terms of this and this. So you have to decide whether your crossing is of type L plus or L minus. But you don't have to remember L0. Remember, when we had the Kaufman bracket, there were sort of two of these non-crossing pictures where you joined strands top and bottom like that, or you could join strands left and right. But with the orientation, you don't have to worry, because there's only one thing that could be L0, because it's got to match the orientations. You see, if you look at the arrows on the left, the only way you can sort of get things correct is to have the top and the bottom joined, because otherwise the arrows wouldn't be consistent. You've got to come in and go out top right, so it has to be like that. So you don't really have to remember L0, it will just follow from the orientation when you apply this formula. Okay, so let's now apply this formula, and so I've done this in the notes for this week. So I want to apply this formula to compute the Jones polynomial of this knot. There's a different way of computing it on the next sheet, on the sheet 5. This is the knot, it's a nice symmetrical knot. It's 5 subscript 1 in the catalogue, 5 because it has 5 crossings. I've chosen you've got two choices of sort of, there will be this knot and its mirror image. It won't be equivalent to its mirror image, so you have to make a choice. So I've made that choice by emphasizing the overpasses. I did that in black, then you couldn't see that, so I put the sort of bridges to emphasize what's going under and what's going over. So what we have to do is we first of all have to, we want to apply the formula. So I used this box for the Kaufman polynomial, but it's now become red to indicate I'm computing the Jones polynomial, not the Kaufman polynomial of this knot. So the thing in the box is meant to represent a polynomial, a Laurent polynomial in T. And the first term of the formula I gave you a minute ago has T minus 1 V of L plus. So is this L, let's fix the crossing. Let's deal, say, with this crossing here. They're all the same, actually. But if we deal with that crossing there, is that a plus crossing? Well, if you look at the arrows, you see it is a plus crossing, because if I think of the overpass as the x-axis going from left to right, then the underpass is going upwards And that's the plus orientation. So it's a plus crossing. The rise is +1. That's the same thing as saying the rise is +1, or the sign. The rise sign, as I explained on the Padlet, is +1. So all the crossings are equivalent here. So the rise is +5 because there are 5 crossings. So that is therefore L. Let me write down the formula again. So it's T minus of V of L plus, and L plus corresponds to when you have the part of the knot which has, it's normally drawn like this actually. Unfortunately here this has been rotated, but you have to learn to recognise L plus as I explained before. Then it would be minus T, so it's really just the part of the knot with that. I mean it's V of the knot, but we're only going to change the part near this crossing. So when we reverse the crossing, we'll get this picture here, and the rest of the knot stays the same. And that's equal to Z with my new notation, little z, times V of L0, which remember, because of the orientations, it has to look like that. Because what's outside these circles has to match the rest of the knot, because the rest of the knot still exists and the orientations have to match up. So you can't change the directions of the arrows coming in or going out of these circles. So that's the Skine relationship, and we're going to apply it to this crossing, this pink crossing. So we have to identify these terms. This is V, this would normally be written V of L minus. So this is V of L plus, this is L minus, and this is L0. Now you might say, why am I using L? Well, L stands for link. Of course, it so happens that we're talking about a knot here, but a knot is a link. But the thing about this formula is you have to use links, because if you look at the powers of T, you may remember that the Jones polynomial of a knot is always a Laurent polynomial in T. On the other hand, Z has fractional powers. So in order to get T in powers of positive and negative powers of T, integral powers of T, we're going to need fractional powers here. So that means when we do this modification and get rid of the crossing, this has to be a link. So when we get rid of the crossing, the thing that results here must be a link, a two-component link. Otherwise the formula won't work. So we're forced into using links. So that means, unfortunately, you need to be aware of some of the Jones polynomials of the sort of simpler links, at least. Or you can look them up, I guess. Now that's a bit of a pain, because a link, if you've got two components, you've got to worry about the orientations, and if the link's complicated, there will be different possibilities. And that is a bit of a nuisance. Anyway, what happens when we do these modifications in this case? Well, I'll make a mess on this page and then change pages. So the first thing we do is we reverse the crossing. So I'm working with this crossing here. So the overpass is going sort of, you can see, but if I reverse it, then this becomes an overpass like that. Okay, that's now, I'm now doing this one. And now I've got two overpasses, and I can just pull that loop down, because remember the Jones polynomial only depends upon the topological class of the knot. It only depends on the ambient isotopic class of the knot. Or if you like, an equivalent way of saying that is you can do any Reidemeister moves and you don't change the Jones polynomial. So we could do Reidemeister move R2 and get rid of this loop and just pull it down, pull it away from the top strand. But it's obvious you can do that if you think of the knot in space. It's just that loop is just sitting on top, so I can just pull it down. So I've now got a knot still, a knot which is going around like this. Can you see what sort of a knot this is? It's a trefoil, because it's got three crossings. I'll show you a better picture in a moment. I've got rid of two crossings, so I'm left with three crossings, and the only thing you have to decide when you say a knot with three crossings, are the crossings alternating? If they're alternating, it must be a trefoil knot. If they're not alternating, it's an unknot. But here they're alternating, under, over, under. So it's a trefoil knot. And you just need to, it's a sort of more or less the standard drawing of a trefoil knot. So if you look at the way the underpasses come out, it looks to me as if it's a right-handed trefoil knot. So this is actually the right-handed trefoil. And then, before I refresh the page, you have to worry about what happens, what link you get when you do this business. Well, what's going to happen is, you look at how it was, you'll sort of have, see if I can reconstruct it here. So we had the knot as it was originally. Sort of 5 loops. Let's not care about the orientation for the moment. So what happens is we were working on this crossing here. So the arrows were going this way round. Is that right? Yeah, because it was coming round like this, and then yeah, it's going that way, round like that, going up like that. So the only thing, there's not much choice, as I explained. You don't, of course, the orientation is now different from the usual formulas I've written on the bottom, because everything's been rotated up there. But you see, with the orientations, you don't have a choice. If you're going to get rid of the crossing, you have to join that strand with that strand, and this strand with that strand. It goes like that. So that's what we have. And what we therefore have is a, let's see, we have this going round like that. I forget which is under and which is over. And we have this going through like that. So it looks to me as if it's a hop link. But we'll see in a moment. No, it's not actually a hop link, it's more complicated, but let's see on the next diagram what happens. It's going to be a link, and in fact one circle is crossing over 4 times. There are 4 crossings. So I've got 4 crossings left, so it can't be a hop link. I've got 4 crossings left, and they're alternate. They're not. They're going to be alternating. I think. So. Well, it looks like actually what I did here, it seems like I was working on the wrong crossing. It's all equivalent, I'm afraid. So let's just jump to this one. Actually, to get this, it seems I worked on this crossing, I'm sorry, but it wouldn't have changed the result because all the crossings were equivalent. So when I worked on this crossing, when I reversed that crossing, I could still pull this loop down because this would have become underneath, so I'd have got 2 underneath instead of 2 on top. So I could still push this little loop down, and that's why I get that picture there. But then I was working on this top crossing, so now the orientations look like that. And you see I eliminated the crossing, and the orientation here was going like this, was going around, then it was going down like that. So the only choice I have is to sort of make it like that. It was much better to work on the top crossing because that then did fit the diagram I had of the Skine relation. Should have worked on that crossing to begin with. It's easier to understand. So you see now what I get is I get a link. The computer automatically changed the colour for me because it's now a link. I've separated the 2 components. And it's this link where you have 4 crossings, and you see they are alternating. So I can't simplify that link, sometimes called Solomon's knot, although it's actually a link, or the duplex knot. So what's the conclusion then? Here's the relationship written out. It means that the t inverse of this minus t of this Jones polynomial minus z, the Jones polynomial of this, is equal to z times the Jones polynomial of this. So that means if we multiply everything by t, what we want, which is the Jones polynomial of 5(1), is actually t squared times, this, remember, is the right trefoil, so it's t squared times that, and then we multiply z by t to the by t, so that becomes that. and I've used this symbol L with 2 arrows like that for this link here, because that's where the arrows are going. Okay, so we haven't finished. We now have to work on the Jones polynomial of this link. Okay, but actually a similar thing was calculated on the last sheet, but it wasn't. It was the same link but with different orientation. So on the last sheet I sort of had one arrow, I had the top arrow going that way and the other arrow going backwards. And we computed the Jones, there was an exercise, maybe you're still doing it, to compute the Jones polynomial of that. And it started, I think, minus t to the 9 over 2, etc., etc. There were 4 terms. Unfortunately, that's not quite right for us because we have this orientation and things were a bit different. There is a problem on this week's sheet to show how you can go directly from one to the other using linking numbers. But anyway, what I actually did in the notes was then did the same trick, the same idea, another application of the Skine relation to work out the Jones polynomial of this. So I don't think I want to do that in detail now, because I want to get on to the other topic for today. But you see, the question is, what is the Jones polynomial of this? This box means I want to compute the Jones polynomial of that link. So I then have to start afresh. There we are, starting afresh. And we start with this. Now we have to do the same thing. We have to work out what crossing to work on. I'm not sure what crossing I worked on. Yes, I think I worked on this crossing this time. This crossing here, so I want to apply the setup to do that crossing. Now, is that a plus crossing or a minus crossing? The arrows are going this way. We've changed things a bit, so it is a plus crossing. So this is indeed, I've already given the game away, so I've got T inverse in front of it. But yeah, that is a plus crossing. We've got the overpass, the underpass coming up underneath in the right direction. So this is a plus crossing. And what happens? Well, we have to work out what happens when we reverse the crossing. Well, if we reverse the crossing, then you see, again, we're going to have 2 overpasses, so we can pull that through. And you can think, here's the red circle, we can just think of it as a circle. We can pull the blue one through, and it's just going to finish up looking like a Hopf link. Okay, so we need the orientations here. So V minus, L minus I should say, we want V of L minus. L minus is going to be this time the Hopf link. L plus was this Solomon's link. Now, the Hopf link, if you don't have the orientations, there's only one Hopf link, because a Hopf link is just 2 circles, yeah.
Sorry, with your L0 from the last thing,
yes.
How come you chose to split it horizontally instead of vertically to make the answer?
Because, you mean this, you're asking about this?
Yeah.
Well, I have to do it like that, because, first of all, if you look at the relation, if you work on the top crossing, which is what I originally did on the notes, and you look at the relation, the Skine relation, which I wrote there, you'll see that the orientations are consistent with doing it like that. So that's one answer. But the more honest answer is to simply say, look at the orientations. You see, I couldn't split it the other way, because the orientations here, I need an arrow going this. I'm just working on this little bit, so I need to make sure that when I've worked on that little bit, I've still got an arrow going that way, and I've still got an arrow coming in that way, so I've got no choice. Okay, that's what I was trying to say. You don't have to remember, you don't have to memorize that last relation, that last figure, because it follows from the orientations. You've only got one choice. Even if things are skewed up, like before I hadn't rotated the diagram, so we'd forgotten the sort of orientations, but you could still work out using the orientations how to get rid of the crossing. Okay. So anyway, in this situation I'm here, and again, just to explain the same thing again, what about L0? we have to, so we have this minus t times this is equal to z times v of L0. So what is L0 in this case? Well, you see the arrows are going this way and they're going this way. So this time I have to split it vertically. Okay, so I would actually split it vertically. Can you see what I'm going to get if I do that splitting vertically? So let's just do it on this diagram here. So this will just go up like this, and this will go up like that. So it's going to be a knot again, because I started with links. So this time this one's going to be a knot. So I'm just going round, just going round like this. Is that over or under? It's over. Under, over, and then I go round again. So again, it's a trefoil knot. Okay, what sort of trefoil knot is it? Looks as if it's a right trefoil knot again. So this is actually a right trefoil. So we can put all that together. As I say, this is all done in the notes. So here are the better pictures. So what do we do now? We wanted to work out the Jones polynomial of this, and now we do actually know what we're dealing with, because the Hopf link, I myself can memorize the Jones polynomial of the Hopf link. You have to decide whether it's a right-handed link or a left-handed link. So I have the arrows like that. And that is a right-handed link, because if I grasp the blue circle with my right hand going round it, then through the middle I've got the red thing should be going that way, which it is. So this is what I would call a right-handed Hopf link. Now, a word of warning, when we talk about left and right trefoil knots, that's got nothing to do with the orientation. I don't need an orientation for a knot to distinguish left and right, because there are two different knots. One is the mirror image of the other. So the left trefoil knot and the right trefoil knot are not ambient equivalent, not ambient isotopic. For the links, the difference between right or left is coming from, in this case for the Hopf link, the distinction between right and left is coming from the orientations. So you might prefer me to call this the plus Hopf link, if you like, because the rise should be +2. Otherwise it would be -2. I call it right-handed because I'm using the right-hand rule. But the left-right business for the Hopf link is coming from the orientations, not from the underlying link itself. But anyway, this is the right-handed Hopf link, so its Jones polynomial has positive powers of t, albeit fractional. The right-handed trefoil knot also has positive powers of t. So if you know those two formulae, you can just substitute that in, and you discover that the Jones polynomial of this Solomon link with the given orientations that we had today actually starts -t to the -11/2. Okay, and you plug everything in, and you can find the Jones polynomial of 5(1). Rather than write that down, I'm just going to give you a table. Are there any questions before I? Yeah.
So do you choose an orientation first and then do
Yes, yes. Because everything, you should be given an orientation, because the Jones polynomial, if it's a knot, it doesn't matter. So I chose it to make it positive because I wanted the one I wanted. No, sorry, the orientation wouldn't affect that actually. Yeah, you choose the orientation. So I think I chose the orientation so I got the arrows going in the nice looking way so that I could apply the skein. Had I used the top crossing, which I forgot to do, the skein relation would have been looking in, as it usually does in the book. Okay, but changing the orientation wouldn't change anything, but it doesn't change the rise. You just choose the orientation that makes it, of the knot, that makes it easier for you to recognise the skein relation. If it's a link, you have to be given an orientation. You have to be given orientations because the Jones polynomial will depend upon the orientations. If there are two components, you can change both of them, that won't affect it. But if you change one of them, it will affect it. So for this link here, if you change one orientation, you actually get t to the 9 over 2 and not t to the 11 over 2 at the start. So it will change dramatically. So if it's a link, you must be given the orientation. If it's not, you can choose it. And then you do for the Jones polynomial, then you do the calculations. If it's Kaufman bracket, you don't need any orientations to start with, although when you convert that to the Jones polynomial, you need the rise, which does require a choice of, to calculate the rise, you need orientations. Any other questions? Okay, so let me just finish this first half. So I'm really dividing the talk today into examples. Here you've had the examples on the how to calculate Jones polynomials using this Skine relationship. Here's a list of Jones polynomials. And let me just make some comments about this list. So, you can imagine in theory if you spent all of your reading week computing using these relations, you could probably build up this list yourself, but it would take, several days. So the one we've just done, if you put all the things together, and you should do this, you should just put the formula in that I've given you, you will come up with the Jones polynomial of the knot 5, 1, and it will begin minus t to the 7th. Don't forget that most of these knots are not equivalent to their mirror images, and if you go to the mirror image, you have to replace t by t to the minus 1. Okay, so when you see tables of Jones polynomials in books, you may well see some of these different because you may see negative parts of t. That doesn't mean it's wrong, it just means they've chosen the mirror image. Because in these knot tables, there's I've come across no rule that tells you when you see a picture of 7, 4, of course there are two knots 7, 4. You can reverse all the crossings and get the mirror image knot. And I don't really know which one they choose in the tables. And I think some people choose different ones. So bear in mind that you could replace t by t inverse and it would still be valid. However, notice that most of these polynomials, they are different when you replace t by t inverse. So that proves that most of these knots are different from their mirror images. There are two exceptions. How many? Can you see the exceptions? We know that 4, 1 is achiral. And of course that is invariant. It has to be the Jones polynomial. It has to be invariant by replacing t by t inverse. There's another one on the list. 6, 3 is also, and that is also achiral, as you might be led to expect. That is achiral. However, when you go up to 10 crossings, I believe there's an example of a knot with 10 crossings for which the Jones polynomial is symmetric, but it's not its mirror image. So be careful, it's not infallible. The other comment is that if you look at these polynomials, forget the red ones for the moment, the signs alternate. They may start plus or they may start minus, but all the powers of t are present, apart from for the red ones, and the signs alternate. Minus, plus, minus, plus. Remember also that when you put t is equal to 1 for the knot, you get 1. You have to get 1. So if you don't get 1, I've made a mistake somewhere. That's easy to prove using the Skine relationship. That's on I think that's on the sheet. A sheet. The red ones don't satisfy that because they're missing a power of t. You see, the 3 red ones, including the trefoil knot, are missing a power of t. Otherwise, all the powers of t occur going from top to bottom. And these 3 examples are examples of what are called torus knots. They're not all torus knots, but they're torus knots in which you have 2 loops. They're knots you can inscribe on a torus, like I did right probably in the first lecture. Torus meaning sort of donut-shaped surface. So these knots, including the trefoil, which was in the first lecture, you can inscribe on a torus. And if you can do it so it just goes twice around the outside, then these are these special knots in red, and they have a slightly awkward, they're missing a power of t. And there is I put a level 7 question on this week's sheet, which computes the computes actually the Jones polynomial of 5, 1. We've essentially just done that today, but it's another method using the Kaufman bracket. And I think that method will actually compute the Jones polynomial of any of these sort of symmetrical looking looping knots, which are these torus knots with two going around the outside. But that won't prove that there aren't other knots which could be missing parts of T. So I don't know how difficult that is, nor do I know how difficult it is to prove that the sides alternate. I think it can be done, but we're not going to do that. Okay, that's all I want to say today on the Jones polynomial. Yes?
So is the Jones polynomial being invariant, so T to T minus T3 in that, just a necessary condition for the not to be carried?
Yes, because when you take the mirror image of a knot, the Jones polynomial changes. If you know the Jones polynomial of this knot, if you take its mirror image, the Jones polynomial of the other one will be obtained by replacing T by T inverse.
So is that not a sufficient condition?
No, it's not. It's a necessary condition, but as I say, there are examples where the Jones polynomial is symmetric in that sense. But so in that case, the Jones polynomial is not distinguishing between a knot and its mirror image, but almost always it does. Okay. As I mentioned before, there are also knots with. It's unknown whether there is a knot. The unknot has Jones polynomial 1. It's unknown whether there is another knot that has Jones polynomial 1. That's an open question in knot theory. And I don't think it's even a conjecture that there is no other, because in the history of knot theory, people have sort of made conjectures and they have found with enough crossings they've found a knot that sort of contradicts the conjecture. So there are knots, and that is also in the notes, this Conway knot, which is on the gate in Cambridge. There are two knots. There are pairs of knots that have the same Jones polynomial, which are not equivalent. Well, I've already given you an example with 10 crossings, there's a knot and its mirror image. But there are other examples with, I think, 11 crossings where two completely different knots, not mirror images, have the same Jones polynomial. But it's quite easy to get links with, I think, Jones polynomial 1. That can be done more easily. Okay, the next topic is, I think, more appropriate really for leading up to reading week, because I find it quite fun to do. It's this notion of encoding knots. So I sort of like this idea because if you did discrete maths with me, you know that when we tried to put graphs on the computer, and I did try and do this myself to try and compute depth first searches and so on, and check what I was doing by hand, the way to put a graph on the computer is to use the adjacency table of the graph. And so we need a corresponding method for knots. How can we sort of input a knot data on the computer? Okay, so this is the point really of the next two sections. One video is yet to appear, but 5.2 there is a video. So there's some overlap here with what I've said in my video. And I want to emphasize that I'm talking about knots, not links. Links would be more, normally there's not much distinction. What I say for knots is often true for links. But I think for this I really need one component. I mean, you can generalize this for links, but I'm worried that I may say things that are not valid for links. So I'm really just talking about a knot. And there's this very neat thing called the DT code. It stands for two mathematicians, Dowker and Sittlethwaite. And this is obtained by essentially just starting at a point on the knot, going all the way around the knot as if you're driving around it, and just putting a number each time you come to a crossing, a successive integer. You start with 1, 2, 3, and you just go all the way around the knot. So if the knot has, don't forget, if the knot has C crossings, you always drive through each crossing twice, once underneath and once on top. So you'll meet each crossing twice. So you need 2 C integers, and then you go back to where you started. So you're going to have integers each time you come to a crossing. You label it with an integer, and you're going to end up with 2 C if there are C crossings, and then you start again. So I'm not interested when you start again. So how does this work? Let me show you for the trefoil knot how it works, and then you'll get the idea. So if I take the trefoil knot, Let's make it, for a change, the left-hand trefoil knot. So I think that means the overpasses are like this. Over, under, over. Second means the overpasses, of course. Now, I need to start somewhere, so let's start here. I always want to start so that my first crossing is an underpass. Okay, so that's what I normally do, or at least if it's an alternating knot. It's slightly easier to do this for alternating knots. If the knot is not alternating, you need to add minus signs, as I'll explain. But anyway, let's start here, and let's just go around the knot. And I want to start with, I want my first crossing to be an underpass, so that means I have to go in this direction. The knot isn't, I mean, I'm choosing an orientation, but I'm really just talking about the knot. So I label this crossing 1. I always like to put my label, this is a personal choice, when I arrive at the crossing, I like to put my label on the right-hand side, because I think of this chessboarding a bit, and, you know, if the diagram is chessboarded, I look to see whether the right-hand region, that would be the third quadrant, is white or black. So I always like to put my number here. I'm not using chessboarding here. And then I keep going, and the next crossing is number 2. The next one is number 3. And then I come back to the first crossing, doesn't matter, it becomes labelled again, number 4. Then I go to then I come around number 5. And I go number 6, and here C is 3, so I've finished. I go back to number 1. So I've labelled each crossing with 2 positive integers. So, for example, each crossing has an odd, because this is an alternating knot, or actually you don't need that, but each crossing will always have an odd number and an even number. So 1 is associated to 4, 3 is associated to 6, and 5 is associated to 2. So these 3 columns really represent labellings. Each column represents a crossing with its 2 labels. Okay? And even if the knot's not alternating, I think because of this chessboarding thing, you'll always go, each crossing will always have an odd number and an even number associated to it. It will never have 2 odd numbers. And so the code, well, we've written the odd numbers in order here. I mean, if there were more, if there were more crossings, it would be 5, 7, 9, and so on. But the even numbers, of course, depend upon the knot picture, the diagram. This is a code of a diagram, really, not of a knot, because if you have more crossings, you'll get a different code. So it's really a code of a diagram. But the code, what is the code? Well, the code, you don't really need to know what. Just remember that 4 goes to 1, 6 goes to 3. So the code, the so-called DT code, is 462 for the trefoil knot. That's it. Simple as that. And I'll explain in a moment how you can reconstruct the knot from this code. So that's the idea. Couldn't be simpler. And that's just a formal explanation of what I've just done. So because the knot was alternating, because my first underpass was 1, all the underpasses are 1. Sorry, all the underpasses are odd, and all the even passes, all the overpasses correspond to even numbers. And so for each crossing, I've associated an odd number to an even number. So I've got a bijection from the odd numbers to the even numbers, and I just take the images in order of the odd numbers, and that is the code, the Dowker, sometimes called the Dowker notation, or the Dowker-Sissel-Waite code of the knot. Okay. Before you ask questions, let me show you how to reconstruct the trefoil knot from its code, or the trefoil diagram, I should say, from its code. So here's the code, 462. So how do you sort of find a knot that represents that code? Well, you start with a little arc here that's going to come into the first crossing. So the first crossing is going to be an underpass, and it's labelled 1. but it's going to be over. Remember, the 4 corresponds to 1, 6 corresponds to 3, and 2 corresponds to 5. So this overpass is going to be labelled eventually also by the even number 4. So I put a 4 somewhere, it doesn't matter where. I don't know I don't know if I'm going to come underneath or from on top, so I just put it anywhere away from the crossing. Then I go to crossing number 2, which is an overpass, and crossing number 2 goes over an arc which eventually will be labelled 5. So I put my 2 there, coming in from the right, putting it on the right as I come in. I'm going in this direction. And then I go to 3. Now 3 is underpassing 6. That's what this notation is telling me. So I've got an arc here which the crossing is also going to be labelled 6. Not the arc, the crossing. I put the number up top because I don't know where to put it at this stage. But then the next label would be 4, but I've already got a 4, so this is when you double back. Now you can double back either underneath or on top. Okay, so you just have to make a choice. Make a choice for me. I didn't hear. Underneath. Okay, so you go that way. Okay, so that means I ought to put the 4 there once I'm arriving like that. That's fine. And then I go to number 5. Well, I've already got a number 5, so I have to just double back here, and I put the 5 down there. That's fine. And then I go to number 6. Well, although the 6 is written on top, it could equally well have been written underneath. So this is also number 6. Then after 6 I finish, so I go back to the beginning. And I also have a choice here. I can go underneath or on top. It's probably neater to go on top. Okay, and that is the trough or not. It's not probably what you expect it to look like, but it's 3 crossings and they're alternating, so it must be a trough or not. Is it a left-hand trough or not, or a right-hand trough or not? Okay, we've got both left and right. Well, I made a mistake actually in my introductory lecture. I got this wrong. On the outside of this knot, you might be tempted to think, if you look at this crossing here, and I'm driving out, as I've told you before, when you drive out, you're verging to the right. So you might think this is a right trophor, but it's not. Because in this diagram, I've only got 2 arcs on the outside. I've got this one and this one. So it's not the usual sort of setup for the trophor. To get the usual setup, I should have, in the final step, although it was much neater to do it as I did it, I should have really gone this way round it to get the usual picture of the trophor. And that's obviously legitimate to do that. Now I've got, although it looks very strange, I do have 3 arcs on the outside of the diagram. And then it is, I think, the usual picture of the trophor. And so if you look at one of the crossings now, let's look at, say, this crossing, and let's look at the arcs on the outside, which are this one here, and this one coming in, the green one coming in here, as an underpass. So that looks to me like it's the left trophor now. Okay, so I claim this is the left trophor. I claim this is the left trophor. However, I could have got the right trophor knot had someone not told me to go underneath to 4. If I'd have gone on top to 4, as I was intending to do because I put the 4 on top, I would have got the other trophor knot. So unfortunately, this Dowker notation, it doesn't really distinguish between a knot and its mirror image. If you 2 knots, a knot and its mirror image can have the same code. Okay. Next thing I want to do 2 more things. The next thing I want to do, there's the example of a figure 8 diagram, but I skipped that. Here's a more complicated knot with, I think, 8 crossings, and it's not alternating. So how do I deal with that? Let me tell you what its code is. You start where you want to, so I think I'm going to start there. My own rule is to try and start with a lot of space to set up my starting gear and so on. So I choose an arc which isn't too crushed. That's just, and I go in that direction if I want to start with an underpass. I don't know if that's essential, actually, but I'll adopt that convention. So first underpass is 1, then I have an overpass which is 2. You can see the overpass is more than me, I think. And then I go 3 as an underpass. And then 4 is sort of wrong, because this is not alternating. I've got 2 underpasses next to each other. So 4, actually, you'd expect it to be an overpass, but in this picture it's an underpass. So I put a minus sign. I associate with 4 the minus sign. When you have an even number, you only worry about the even numbers, because those are the ones that are going to appear in the code. So it's only the even numbers that have the minus sign. I mean, I could put a minus sign with the odd number as well when I get to it, but I'm only going to record the even numbers. So I put a minus 4 there because 4's underneath. And then it's 5, 6 is over, 7, 8 is over, 9, I don't care whether 9's over or under, 10 is over, 11 is under, 12 is under, and it should be over, so in a sense it should be over. So it's 12 minus, or minus 12, because it's going underneath. And then it's 13, 14, 15, 16, and then I'm finished because I only had 8 crossings. So the DT code is actually, so I have to work out what's associated with 1, that's 6, so the DT code is 6, 3, don't forget it's 3, I don't look at 2, I'm looking at the odd numbers. 3 is associated to 8, shout if I get a mistake. 5 is associated to minus 12. 7 is associated to 2. 9 is associated to 14. 11 is 16. 13 is minus 4. And 15 is 10, and that's it. So that's the code. Now most people write it like that, but I like to put commas so there's no confusion. And you don't normally put brackets, but you can if you want. Okay, so it's actually the method. And then you can go and reconstruct it. If you reconstruct, you won't get a diagram that looks like that, but you just have to remember when you see a minus sign, you've just got to be underneath. The odd one will be on top. Okay, I wanted to do one final example. Of reconstructing. So I want to, here's a knot with 6 crossings with DT code 6, 8, 6, 12, 10, 2, 4. And let me try, and this is obviously more complicated, let me see if I can reconstruct this. So of course any permutation of the first 6 even integers will actually give rise to a knot. It will always work, the reconstruction process. It's not completely obvious why, but it will always work and give you a knot with 6 crossings. But many of them will not have crossing number 6, they'll be more simple. And there aren't many that sort of give you the best knot, the knot you want. Anyway, with this code, it will be a knot with crossing number 6. And how do I do it? So I start with 1, crossing number 1, which is overpassed by an arc which eventually will be labelled 8. And then I go to 2, which overpasses, and I have to put my odd numbers up top, otherwise I make a mistake. So 2 will be overpassed by 9. 2 will overpass 9. These are crossing numbers, not arc numbers. And then 3 goes underneath. It's alternating because there are no minus signs. 3 goes underneath a crossing which will also be labelled 6. And then 4 goes over 11. And then 5 goes under 12. I've got to check I've got not going back yet. 5 goes underneath 12. And then 6. So I do have a 6. So this time I won't ask you, I'll just go on top. So that brings me round to 6, which I'll put there in the right position. And then I go to 7. Now I don't have a 7, so I'm going down 6. 7 will be overpassed by a 10, which I don't have yet, I don't have already. And then I go to 11. So I've got an 11 here. So sorry, this is 7. Now I'm going to 8, sorry. I'm going to 8, so 7 goes to 8. I can join that up. 7 goes to 8, so I guess I can do that. 8 goes to 9. Well, that's convenient. 9 goes to 10. You see how it's working out miraculously? I don't have any sort of loose ends. 9 goes to 10. It should be put there. And then I go to 11. And then the 11, even here it works out. The 11 goes to 12. And the 12 goes to 13, but I'm back to where I started with because 13 is, I only have 6 crossings. So there's my knot. Okay. Now you might ask, what the devil is this knot? Well, you can work out quite quickly what it is by doing the following. First of all, I'm going to chessboard it with white on the outside. So that means that, I'll be very quick here, that means that this will be black, pink in this case. Any regions that have an edge with the outside will have to be darkened. And now, you see, this diagram is a reduced alternating diagram. So this is a reduced alternating diagram. So we can actually work out what if we want to call this diagram D, we can work out the Kaufman bracket. But we can at least work out the highest and lowest powers of A in the Kaufman bracket. And the highest power of A you get like this. There's a formula. If you look in the last week's work, explained this in the last video last week, there's a formula which is the number of crossings plus twice the number of white regions. So how many white regions are there? There's the outside, 1, 2, 3, there's 4. How many black regions are there, or pink regions? There are 1, 2, 3, 4 again. So the highest power of A is actually, in this case, 6 plus 8 minus 2, that's 12. So this will actually start A to the 12. There may be a sign here. In fact, I think there was going to be a minus sign there, but I don't have time to check that. And then the lowest power of A, it's the same calculation, it's all symmetric because the number of black regions and white regions is the same, will be A to the minus 12. I think now the rise you can compute is 0, because there are 3 plus signs and 3 minus signs in this case for this diagram. So actually we can convert that straight away into the Jones polynomial. To Jones polynomial, we just replace A by, I think these are minus signs, we replace A by t to the quarter, minus a quarter. So this becomes minus t to the minus 3, and this becomes minus t cubed. And then we don't know what's in the middle. But just the chessboarding has enabled us to get that much information on the Jones polynomial. And now the only last thing I have to do is find my table, which I've lost. I'm just checking the signs here. Yes, so if you look at the table, the only Jones polynomial with 6 crossings is 6, 3. I've even got the signs right. Okay, so this will tell you that the knot, in our case, is essentially 6, 3. And we don't even have to worry about mirror images because that's achiral. Okay, I'll stop now.